All right, so let's go ahead and get started with where we left off last time. So what we were doing was going through this interpretation of the deformation gradient as as a combination of rotation and stretch. Um, so I told you that V could be decomposed in this form, like R times U tensor or V times R tensor, which meant that basically if you decompose F as R times U, then the U tensor, which is a symmetric and symmetric stretch tensor, it acts upon DZ vectors. Those DZ vectors um, are these undeformed tangent vectors. Then U tensor acts on those, stretches those corresponding eigendirections of U by an amount UN1, UN2, UN3, where they came out to be lambda times N1, lambda 1 times N1, lambda 2 times N2, lambda 3 times N3. And once all of the stretching has happened in these three directions, then the rotation tensor acts on that and gives you this final deformed configuration of these tangent vectors. The other way to think about it was, if you were to take the undeformed tangent vectors, you rotate them to their final correct directions first, and then you do the stretching by the V tensor to stretch them into their corresponding amounts. And we went through an exercise last time of how to find these V and U tensors by basically noting, first of all, that the B tensor, which was F transpose F, is equal to V squared. So if I calculate the eigenvalues and eigendirections of the B tensor, then the eigenvalues of the V tensor would be the square root of that, and the eigenvectors would be the same. Similarly for U, if you know the C tensor, you can calculate its eigenvalues and eigendirections, and the U tensor has the same square root of the eigenvalues and the same eigenvectors. And once you have V or U, you can use the expression for F to calculate the rotation tensor. And we went through an example in MATLAB for the simple shear example, where this example is posted on Blackboard. So you can take a look at that and try to understand. And if there's questions, obviously either post them to the discussion forum or bring them to my office hours. So maybe at this point, are there any questions about anything in the class? And Hugo, you would have to help me to address those. No questions?
No question.
All right. Okay, so let's keep going. So what we did there was what is called the polar decomposition of F. Now there is something called the pseudo spectral decomposition of F. It's the same F tensor. Maybe let me ask the class a question. Can we do a spectral decomposition of F by finding out its eigenvalues and eigenvectors? Do you think we can find eigenvalues and eigenvectors of a general F tensor which may not be symmetric?
They say no.
Okay, that sounds good. Yes, indeed, since the F tensor in general will be non-symmetric, so if we were to find eigenvalues and eigenvectors of an F tensor, a general F tensor, they may come out to be complex. So the way that we had studied eigenvalues and eigenvectors of a tensor was for symmetric tensors. So let's see if we can come up with something similar for this deformation gradient tensor. Since it's not symmetric, but we do know that it has certain key directions in which it causes maximum or minimum stretching. So what we can do is actually set up something called a pseudo spectral decomposition, where if you look at this if you look at this expression, f acting on a ni vector gives me a corresponding mi vector stretched by lambda I. So let's pick one of the directions, n1 for example. So f acts on n1, and what it does is it stretches it by an amount lambda 1 times n1, and it also rotates it and puts it in the direction m1. So hopefully this idea that f acts upon n1 to stretch it and rotate it to put it around lambda 1 times m1, where both n1 and m1, they are both unit vectors. So hopefully you can see that for these three particular directions, n1, n2, and n3, the F tensor acts on them and it stretches them and does a rigid body rotation to their final configuration, right? So that's what I'm showing here. So using that as the basis, we can come up with this pseudo-spectral decomposition, which says that F tensor can be expressed as the sum over I going from 1 to 3 of lambda I mi dyad ni. Can anybody tell me what's the difference in this pseudo-spectral decomposition with the conventional spectral decomposition of a tensor? If you remember the conventional spectral decomposition of a tensor, both of these vectors were the same vector, right? It used to be lambda I times ni dyad ni, for example. But here we have two different vectors that have a dyadic product between them, and they give us a they define this tensor. So everybody still with me?
Yeah.
Okay.
Yeah.
All right. So one way to check this would be to actually act it upon one of the, let me pick a green color here, to act it upon some nj vector. So let's say I'm trying to take this tensor acting on on nj. So maybe I'll write f acting on nj would be equal to sum from I going from 1 to 3 of lambda I and mi dyad with ni, and let me move this guy a little bit. And acting on nj. So if I compute that, the dot product of ni dot with nj is delta ij, and then I can contract out I to give me this I, this I, this I go away, and they all get replaced with j's. So what we get is that this is equal to and this I as well, actually, the summation of this I. Wait. So this gives me lambda j and mj, where I should mention that there is no sum on j, right? Some discussion going on in the classroom?
You want to
Can you hear me?
I can hear you.
Okay. So how come you can contract out the lambda I and the mi with one delta ij?
Right, because what we are doing here is not using the summation convention because of I have to explicitly write out the summation sign, and even though since okay, so there are, you see that there are three i's here, right? 1, 2, 3 i's here. So I have to have that summation sign because of these three i's. Now the contraction part is still works exactly the same way, and if you kind of lay out all the three terms of those of that expression, lambda 1 times m1 diad n1 plus lambda 2 times m2 diad n2 and lambda 3 times m3 diad n3, you'll see that you still have that fraction sitting up here, lambda I1 or lambda 1j, lambda 2j, lambda 3j. So all of those expressions, out of those three terms, only one of those terms will be non-zero. So you can still apply the contraction even though there are these three i's sitting out here, and what you will get is only one of those terms is the non-zero term that remains, and the non-zero term that remains is mj, the jth term, for which I took for which I was applying the f tensor. So this is also one way to, I mean, it's easy to interpret because you can clearly see that this fn acting on nj gives me lambda j, mj is the exact same thing that I had written up here. If you just replace j with I, you get this, right? So, so this was just a verification that indeed if I take f defined in this way and take that f acting upon some nj, one of this n1, n2, n3, then the result would be the corresponding eigenvalue times the corresponding rotated eigenvector. Rotated eigenvector, this mj is the eigenvector of B tensor, if you remember. All right, so let me keep going with that. We can also check the action of f on some arbitrary tensor u. So f acting on u, what I'll do is I'll write f in exactly the same way, the pseudo spectral decomposition that I wrote out here first. So lambda I mi dyad ni, and acting on u, so that thing in the square brackets is f, and acting on u, I'll again use sum of, let's say, j now. So j going from 1 to 3 of uj nj. And again, if I take the dot product of ni and nj, I get delta ij. Again, I will start contracting out. These j, for example, here. So if I do that, we can cross out this j, replace it with I, and what that would result in would be lambda I times ui, and in the mi direction. And actually I have not contracted out the sum over I, so I need that as well. Sum of I going from 1 to 3. So now this is also, there is a physical interpretation to this. What we are doing is, well, let me ask you this. What is, what is this quantity ui? Since I decomposed u as u, j, and j, ui is nothing but the ith component of the vector u along the direction ni. Okay, so for a general vector in this undeformed space, if we take the components of that general vector along n1, n2, n3, then the effect of f on that general vector is to just scale the corresponding components un1, un2, un3 by lambda1, lambda2, lambda3, and then put them along m1, m2, m3 direction. So all that we did here was to just verify that f acting on a random vector u can again be described using this pseudo spectral decomposition. Where again in this pseudo spectral decomposition, the good thing is that lambda is a real value, and the eigenvectors also have real components, unlike the eigenvalues and eigenvectors of a tensor that is non-symmetric. All right, so this is just yet another way to think of f, and related to the pseudo-spectral decomposition of f, we also have the pseudo-spectral decomposition of the R, the rotation tensor, that f equal to Ru tensor. Can anybody tell me what is a good property, or what is the main important property of that rotation tensor? Is it symmetric, for example? Is R symmetric?
Orthogonal?
Yeah.
They said orthogonal.
Right. So R is orthogonal, and in general, it is not symmetric. In a special case where there is no rotation, R could be identity, and only in that case it's symmetric. So just like the F tensor is not symmetric, R tensor is also in general not symmetric. And using the same concept of pseudo-spectral decomposition of F, we can come up with the pseudo-spectral decomposition of R, where we write this in exactly the same form, well, very similar to the same form as F, except there is no lambda I. Anybody tell me why there is no lambda I here in the pseudo-spectral decomposition of R?
Because there is no stretch.
Right. There's no stretch. It's a pure rigid body rotation. So the eigenvalues, so to speak, of R are 1 in all three directions. It's just a rigid body rotation. All right. Very good. So let's keep going. Now we talked about the C tensor and the U tensor last time. The deformation. This is the F transpose F. So this was F transpose F, and it was also equal to U times U, which is U square. There's a very nice physical interpretation of the invariants of these tensors. So let's take a look at the three principal invariants. These are the principal invariants of these tensors. The first three are for U, the next three are for C. Okay, and to understand this physical interpretation, we are going to make use of the same type of physical interpretation of the invariants, the principal invariants of a general tensor we did maybe some time ago. That if we consider like a unit cube that is oriented along the n1, n2, n3, the eigen directions of the C tensor or the U tensor, the eigen directions are the same. The effect of F is to stretch n1 by lambda 1 and then rotate it and put it along along m1 vector. Same thing for n2 and n3. They go to lambda m2, lambda n3. All the while, the angles between them stay 90 degrees. Here's the question. If I randomly pick some other two vectors, will the angle between those two vectors change? Yes.
Yes.
Yeah, the angle between, in general, the angle between any two other vectors would change, because it's only the eigen directions that for which the angle does not change, they remain at 90 degrees. And as we saw in the simple extension example a while back, the angles between any two other pairs of vectors does change. All right, so what this allows us to visualize is that this unit cube of side 1 goes to a cuboid of sides lambda 1, lambda 2, and lambda 3, right? So let me ask you this. The first principal invariant of the C tensor would be lambda 1 square plus this should be lambda 2 square plus lambda 3 square. I hope you all agree that this would be the first principal invariant, because lambda 1 square is the first eigenvalue of C, lambda 2 square second eigenvalue, lambda 3 square is the third eigenvalue of C. What does this quantity physically represent? Lambda 1 square plus lambda 2 square plus lambda 3 square, given that this is a cuboid of side lambda 1, lambda 2, and lambda 3.
So
Anybody thought of this answer? How about?
So it's going to be the square of the cubic.
Mm-hmm.
The diagonal word, but
That's right. It's the square of the length of the diagonal of opposite corners of this cuboid, right? It's just the distance between that point at the origin and the opposite corner here, because each side is just lambda 1, lambda 2, and lambda 3. The initial length of those sides was 1, so the final length of those sides is lambda 1, lambda 2, lambda 3. So indeed, the first principal invariant of C is equal to or is proportional to the change in length, of the diagonal at the point. So first principal invariant is proportional to the changes in length, and no surprise here. The second principal invariant of U, for example, I think we saw this with general tensors as well. Lambda 1 times lambda 2, that's the area of the face lambda 1, lambda 2. Lambda 2, lambda 3, lambda 3, lambda 1, they are the areas of the other two faces. So second principal invariant of U is proportional to changes in area of the body at that point. And finally, lambda 1 times lambda 2, lambda 3 is the volume of this new cuboid. So third principal invariant of U is proportional to changes in volume. And this is something that we looked at tensors before as well. But this is sort of a nice way to understand it with actual deformation, because now these things are now these vectors are tangent vectors in the undeformed configuration of a body at a point, and the corresponding deformed tangent vectors of a body at a point. Any questions at this point?
No.
Okay. All right, so we'll keep going then. Let's see if we can bring these ideas out with an example shortly, but I'll introduce yet another quantity of kinematics that sometimes is helpful, and this will be helpful in correlating excuse me, correlating the conventional definition of strain that you might be used to. So we know that the map is equal to, or maybe what we can define is a displacement. The displacement field is equal to, if you remember, we said U, displacement field is equal to final position minus, initial position, right? And since X is equal to phi, I can write that as phi of Z minus Z. So if I just rearrange that, I am writing it as phi is equal to Z plus U, right? If you give me the original position of a point, I add the displacement U, then that gives me the final position of the point. Now F, the deformation gradient, was the vector gradient of this vector field phi with respect to the Z with respect to the z coordinates, the undeformed coordinates, that can be expanded using this as follows. So if I take the gradient with respect to z of z, what do we get? Gradient of z with respect to z, that would just be the identity tensor, because hopefully you see that partial derivative of zi with respect to zj is going to be delta ij, and delta ij would be the components of I. And similarly, what we have in the next term is gradient of the u vector field with respect to z. So, and that would again be a tensor. So yet another way of representing the f gradient, deformation gradient, is that it's equal to I plus grad u. And I'll put a grad underline under grad as well, just to keep it consistent with our notation. So this is also a useful relationship that a lot of people use sometimes. I'll write that as a tensor and make that something like this, highlighting that importance. Now, what is the physical interpretation of this gradient of u vector, gradient of u vector field? Let's try to understand that. So we have some body that undergoes that deformation to this blue configuration. At a given point, I have that ball of arbitrary unit vectors, unit tangent vectors to undeformed curves that goes to an ellipsoid in the deformed configuration. Now, this is a messy picture, so let me try to explain that a little bit. There is an original black sphere of arbitrary vectors here. Hopefully you can see that, see that in the background here. That black sphere of arbitrary vectors went to this blue ellipsoid of these deformed tangent vectors. And now what I'm doing is basically starting from, let's say, this n1 that was the original undeformed tangent vector, and I'm connecting that to its deformed, the tip of the deformed tangent vector. So all I'm doing is connecting n1 to fn1. And what this vector does is basically, it basically is the gradient of the displacement field. So if I do that for all of these vectors in this entire sphere of black vectors connected to the corresponding ellipsoid of blue vectors, then what I get is this bunch of red arrows. Those are what are marked out here. And the next step is, what I will do is I'll collect all of those red arrows and make the starting point or the tail of those vectors exactly the same. So what we get in that case is this new red ellipsoid, which is the set of the vectors which basically connect the deformed or the undeformed tangent vectors to their corresponding deformed tangent vectors. And that is a good way to sort of interpret this new thing, this new quantity that we have introduced here. This is the gradient of U tensor. It has again the same eigen directions and different eigenvalues, but the physical interpretation is that it connects undeformed tangent vectors to the deformed tangent vectors. All right, so let's see how it is related to our conventional definition of strain. You remember we said that the green Lagrange strain is equal to half of C minus I. I'll come to that in a little bit. Let's try to express that strain in terms of this new gradient vector that we have defined. So C is equal to F transpose F. All I'm doing is substituting F transpose. This is F transpose out here. This is F So F transpose acting on F should give me C. If I expand it out, I get I transpose I, which is nothing but I itself, plus I acting on gradient of U, plus gradient of U transpose acting on I, which is nothing but gradient of U transpose, and plus I get some term that is gradient of U transpose acting on gradient of U. Okay. Now, an important point to note here is that the deformation tensor C is proportional to U. Of course, it should be. It's a the U is called the displacement gradient. So there was a deformation gradient F, and this gradient of U is called the displacement gradient. But it's also a non-linear function of displacement. So this term right here, which has two U's in it, this is what makes it non-linear. So this deformation tensor C is actually is a tensor that captures the geometric nonlinearity. For those of you who might be familiar with nonlinear deformations, there are primarily two types of nonlinearities. One is called a material nonlinearity, where the material itself, the stress-strain relationship between them is not linear, it's nonlinear. The other type of nonlinearity is this geometric nonlinearity, where you capture P delta kind of effects. So this is what accounts for that geometric nonlinearity, this last term. Everything else is still linear. So using that definition, if I now write C minus I, then this I goes away, and what I have is half of gradient of U, and I'm sort of not writing them as underlines, but only treating the whole thing as a tensor. So I'm making that assumption here, gradient of U plus gradient of U transpose plus this nonlinear term, gradient of U transpose times gradient of U. Okay. Now, what you might be familiar with from maybe your undergraduate mechanics of materials course is a definition of strain which we call the linearized strain. This is the full nonlinear strain. But if I neglect that nonlinear term, if I remove that, what I get is something called a linearized strain, which is half of grad U transpose plus grad U. And I don't know, maybe let's see if somebody remembers, if we have a three-dimensional problem, then the components of the strain tensor were given by partial of U1, partial of Z1, partial of U1, partial of Z2, partial U1, partial Z3, partial U2, partial Z1, partial U2, partial Z3. Does anybody recall this? Sorry. Partial U2, partial Z3, and finally partial U3, partial Z1, partial U3, partial Z2, partial U3, partial Z3. Does anybody recall this definition of strain, where if you remember from the diagonal components, these diagonal, sorry, this should be 2. These diagonal components were the normal strains, and the off-diagonal components were the shear strains. So this was hopefully something that you have seen before in your sophomore or junior year in mechanics of materials. For a three-dimensional body, the strain is defined in this way. And if you try to correlate it to your one-dimensional definition of a strain of change in length over divided by initial length, that would be just capturing that first term. And maybe if you go back to the very first thing that we did out here, Stretch was defined as final length divided by initial length. So strain, the engineering strain, delta L over initial length would be D, the final length minus initial length. That's the displacement over the initial length. And if I try to find the instantaneous strain at some point in the bar, then that would be instant displacement of that point divided by the infinitesimal vector dz in the undeformed configuration. So what I'm showing you here is just that one component, one component, for example, in a 1D problem is correlated to your engineering definition of strain of delta L over L. But in 3D, you should have seen something like this in your mechanics of material class. But that again is a special case of this definition of strain that also works for large deformations that we came up with. So if you neglect that nonlinear term, you come up with this expression. And actually, what I should write there in my this is not epsilon, this is gradient of u. This is gradient of u, and if you take gradient of u transpose, so gradient of u plus gradient of u transpose, and take the half of it, then what you get is your conventional definition of strain. All right, so this was just to show you that whatever you learned back in your undergraduate is a special case of the fully nonlinear, geometrically nonlinear definition of strain that we have just come up with. This is the definition of the Green-Lagrange strain, what we defined, and it does have a nonlinear term. If you neglect that, you come up with your old definition of strain. And let's see what is the consequence of this in the last 2 minutes that we have. Let's consider this map, which is also an example problem in your textbook. I have a unit square, and the map just does a rigid body rotation of this unit square, and then it translates it to this new position by u in the x direction and v in the y direction, or x1 and x2 directions. So the map is given by this long expression. This is the x1 component. Maybe I'll write that. That's the x1 component. That's the x2 component. And z3, there is no change. So that's the x3 component. You can see that for deformation in the x1 direction, we are displacing, doing a rigid body translation by an amount u, plus a rotation of this, the cosine and sine terms help us rotate the z1, z2 coordinates to x1, x2. All right. So knowing that that's the map, if I subtract out z, I can write that map as z plus the displacement map. So everything here that is underlined in the z and in the z3, or sorry, in the red components, is the displacement map. So if I want to take the displacement gradient, that would give me just derivatives of these things with respect to z1, z2, z3. So let's see what those are. If I take the derivative of this first term with respect to z1, what do I get? Cosine theta minus 1. Derivative of this first term with respect to z2, minus sine theta. So that's minus sine theta. There is no z3, so the third term is 0. Similarly for z2, for u2, derivative with respect to z1 gives me sine theta. And derivative with respect to z2 gives me cosine theta minus 1. And no z3. And finally, in the z3 direction, it's all zeros. So we get all zeros here. And now that we have gradient of u, I can compute the f tensor, which would be just I plus gradient of u, meaning just add 1 to the diagonal. So we get cosine theta minus sine theta, 0, sine theta, cosine theta, and 0, and 0, 0, 1. That's my deformation gradient, which you could have directly obtained from the expression of the map up here. You can verify that's the same. And if you take F transpose F, that will come out to be 1, 0, 0, 0, 1, 0, 0, 0, 1, the identity tensor. Why does the deformation tensor come out to be the identity tensor? Because there is no deformation. It's a rigid body rotation and translation, right? At each point in the body, there is only rigid body rotation. And finally, if you compute the strain, the way that we have defined strain, half of C minus I, we get the zero, not vector, tensor, zero tensor, which makes sense because there is no deformation. On the other hand, if you were to use your old definition, the linearized strain definition of the linearized strain, where you take only gradient of u plus gradient of u transpose, and half of that you can compute it, and what you would end up with is something like this: cosine theta minus 1 cosine on the diagonals, which if theta is small goes to minus theta square over 2, minus theta square over 2, and even this definition is clearly not 0, right? So this is not 0, and it's approximately equal to 0 only if theta is very, very small. So your conventional definition of strain tells you that there is some strain even in the case when there is a pure rigid body rotation. So your conventional definition of strain is not correct. Whereas the definition of strain that we have defined in this course as half of C minus I does tell you that for a rigid body rotation, the strains are 0, as they should be. All right, so I think we'll have to stop here, and we'll try to do this again on Wednesday next week, and hopefully we'll be able to set it up much sooner. So all right, any final thoughts, Hugo?
There is any question? I think we are fine.
Okay, all right. I'll talk to you all then on Wednesday next week. Have a good break, and we'll continue on next week, Wednesday. Thank you. Thanks, Hugo.
Okay.
Bye-bye.
Thank you very much.